So we have last time seen a bunch of examples of metric spaces. We'll see a much larger bunch soon enough. But we did not prove they are metrics. I just sketched it. And as I said, there are three properties of metric spaces. And two of them are typically quite easy as long as you get the definitions correct. Okay, so sometimes you have things that are not symmetric, or positive, but usually they are, and it's quite easy to check. Okay, but the third one has some details, so let's look at them. So if you remember, we had three metrics: d2, d1, and d infinity, and they're all of the same nature. Okay, so these are all from norms. What I mean is that if I look at all of them, they can be written in the following form. We can write dp, so that is for p in equals 1, 2, and infinity, and you might guess many other values, actually anything between 1 and infinity. We have such things, but the ones we have defined are all of the following form. That if I have dp of x1, x2, xn and y1, y2, yn, they can be written in terms of vector operations. I look at the difference between these two vectors. Okay, so if I call this vector, let's say x, and I call this y, so this is going to be LP of y minus x, or x minus y, it doesn't matter because these things will be symmetric. So this is, remember, y1 minus x1, etc., yn minus xn, where the three cases have the following values for p. First of all, L1, where L1 of, now I have to say what L1 is of a vector. If I look at the vector with coordinates u1, u2, un, by the way, you have to write, strictly speaking, brackets of a single function, but we'll often write it as a function of n variables with this understood. So this is going to be sum of I equals 1 to n of mod of ui. And so this gives you the differences. These L2 of u1, un. Remember, L2 had a square root of sum of squares of differences, but the differences are absorbed here. So it's sum I equals 1 to n of ui squared. Because square is positive, I don't have to say mod, but I take the square root of this. And finally, L infinity of u1 to un is going to be the maximum over I. So this is maximum of mod of Li, where 1 is less than or equal to I is less than or equal to n. So these are the three distances. And what do we have to verify? So to verify a metric, or indeed I can say if and only if. So suppose we have any function like this. This time it's a function on Rn. So all these are functions Lp which will map Rn to, in fact, non-negative real numbers. We can check that. And from these we can get a metric. So in general, any such function gives you a metric by looking at the difference by using this corresponding formula. But that such a function need not be a metric. It has to have certain properties. So you can say, so if L maps Rn to R greater than or equal to 0, and D is defined by the following. So D of x1, xn and y1, yn is going to be L of Rn. Well, I'll write it in a simpler form. I'll write it as, to be consistent with the above, I'll say y1 minus x1, yn minus xn. So I have a function from Rn which is going to be a norm-like thing. It tells you the size of a vector. If I have this, so if this has, and I have this D which is defined as this, is a metric if and only if the following translation of the three properties hold. So the first property says that if the distance is 0 if and only if the vectors which are the points here are equal, but that's the same as saying the difference is 0. So this says that L of u1 un equals 0 if and only if the tuple u1 un is the 0 vector. Okay, second. Now the second property that we had was symmetry, and that is symmetry. L of minus x, let's say, equals L of x for all x in Rn, for all vectors x in Rn. Okay, perhaps I'll call it V or something because x looks like our whole topological space. So for the vector V, so I'm sorry, L of minus V is L of V. It has to be symmetric. That's why we had to take the absolute values. It has to be non-negative for all V in Rn. And the third property is what is the translation of the triangle inequality. And that says that if I look at vectors V and W, L of V plus W is less than or equal to L of V plus L of W. Okay, it's easy to see the triangle inequality translates to this. You can go back to you can look at this definition. First of all, just putting x equals 0 in the triangle inequality will give you this property. So distance from 0 to V and distance from 0 to W is this way. Okay, and in general, if I have 3 points x, U, V, and W, if I have 3 points here, which is U, V, and W, then this distance is going to be, so I have 3 distances here that are relevant, and this distance is going to be, oh, my U and V look too much like each other. So let's change them to P, Q, and R. Then this distance is going to be L of P minus Q. This distance is going to be L of Q minus R. And this distance is going to be L of R minus P. And we notice that the sum of these two, and R minus P, is P minus Q plus Q minus R. So we apply this equation with this guy as V, take this as V, and take this as W. Then the equation 3 there exactly gives you, this is V plus W, will exactly give you the triangle inequality for arbitrary points. Okay, so these are the conditions we have to verify, and I'll just say here, I'll just write 1, 2 easy for L1, L2, and L infinity, because in all cases, well, in the first 2 cases we are taking the sum of positive numbers, and in the third case the maximum of them. I'm sorry, I should say non-negative numbers. So this is 0 exactly when all of them are 0, whether it's the maximum of non-negative numbers or the sum, or the sum of squares. This is 0 if and only if all of them are 0. Okay, so that is the first property. And symmetry is because we always started by taking absolute value or square, so it's clearly symmetric by construction. Okay, so we must verify 3. Yeah, the only other example we considered Sncf Metric, I will leave as an exercise. It's an interesting exercise. We'll come back to I'll make some comments after we deal with these examples. Okay, so let's first deal with these examples. L of V plus W is less than or equal to L of V plus L of W in the case of all 3 metrics in succession. So here, how will we deal with them? First of all, L1. Okay, so here remember L1 of U1 UN is sum of mod UII equals 1 to n. Okay, L1 is actually quite straightforward. So remark, first of all, you note that mod A plus B is less than or equal to mod A plus mod B for all A, B in R by checking cases. There are 3 cases depending on the signs of A and B. Okay, strictly speaking 4 cases, but by symmetry really whether the signs are the same or different, and if they're different, if they're the same, whether they're positive or negative. But if the signs are the same, both sides will be equal. If they're different, the left hand side will be strictly less than the right hand side. Okay, and if it's 0, you can assign random signs and the same argument works. Okay, and now we can just check. So L1 of, if I look at the sum, which is U1 plus V1 and so on plus UN plus Vn, or not plus, but comma, these are the coordinates, comma, comma. This is sum of I equals 1 to n of mod ui plus vi, which, as we just commented, is less than or equal to sum I equals 1 to n of mod ui plus mod vi, which now we simply regroup and note that this is a sum of two different terms. So this is sum of I equals 1 to n of mod ui plus sum I equals 1 to n of mod vi, and this is just norm u, L1 norm of u. Oh, I'm sorry, so I automatically wrote this, and let me write that on the other hand side too, the vector u and the vector v. Okay, so L1 is actually also denoted as we can put it on top. This is denoted as the norm L1 of the vector u. Okay, where vector u is u1, u2, u tilde. So here I started writing it this way. So this is the norm of u tilde plus v tilde and the L1 norm of it. Okay, L1 is straightforward. L infinity is actually also straightforward, but we have to, it's worth writing this a little bit cleanly. So you remember that L infinity, so just remember that the L infinity function, or the L infinity norm of u1 un is just the maximum of mod ui. Okay, therefore mod ui is less than or equal to L infinity of the tuple u1 un for all I. Okay, and similarly mod of vi, if vi is another vector, is less than or equal to the maximum of these values, v1, vn. Okay, therefore if we look at the sum L infinity, but first let's look at it coordinate wise. So therefore mod ui, mod of ui plus vi, well, we know this is less than or equal to mod ui plus mod vi. Okay, and this is less than or equal to, so mod ui is this and mod vi is this. So this is less than or equal to, let me write it in short, infinity norm of u plus infinity norm of v for all I. And now what do we know? Well, a simple fact is that if a whole bunch of quantities are less than or equal to something, and that's a fixed number, then so is the maximum. So that means that if I look at norm of ui, the vector u plus v, this infinity norm, this is going to be the maximum over I of mod of ui plus vi. But each of them is less than this, so the sum is also less than this, u tilde infinity plus norm of v tilde infinity. Okay. I have been using the term norms. These are all norms. The homogeneity property we don't use as far as metrics are concerned, which is convenient because can look at more general examples which do not have homogeneity. But still, this kind of a metric property holds. So we have dealt with in some sense the two easier cases, L1 and L infinity. The even harder cases are all the P's which require the Hölder inequality. But L2 requires Cauchy-Schwarz, which is subtle, little subtle, but very important. So we'll look at that in a little bit of detail now. Now the L2 case is the actual norm in a sense. So L2 of u, okay, this is square root of norm, so this is square root of sum I equals 1 to n of ui squared, and at this stage it's best to use some linear algebra. Okay, so this is square root of the inner product of u and u. Yeah. So I'm going to assume linear algebra. If you're not familiar with this, it's better to learn it first before dealing with topology. So this is actually called norm u, which is norm u2. So the usual norm which we have in mathematics, geometry, also physics, which is the square root of the inner product, is the L2 function that we have here. So what we have to show, I'll call it a proposition here, norm of u plus v is less than or equal to norm u plus norm v. Okay, where these have now become vectors. So let me just sort of underline them to put some emphasis on this fact. These are the vectors. We have to show this. Okay, proof. Well, this is equivalent. Proof. So the statement claim is equivalent to, let's square both sides. They're both non-negative numbers. Norm of u plus v squared is norm u plus norm v, the whole square. But this is inner product of these two. That is the inner product of u plus v with u plus v is less than or equal to, let's expand this out, norm u squared plus norm v squared, and the cross term 2 times norm u. Okay. Now this is equivalent to, let's expand both sides. So inner products satisfy the usual properties of squares. So we get uu, which is norm u squared, plus norm v squared. And we get a cross term, 2 times inner product of uv, which may actually be negative, though the sum is always positive, is less than or equal to norm u squared plus norm v squared plus 2 times norm of u times norm of v. At this point, you recognize things have simplified a lot. So these two cancel across the sides, and then we can cancel the 2's that are left here, and all we know is that the inner product u comma v is less than or equal to norm of u times norm of v, which, as I mentioned last time, this is the Cauchy-Schwarz inequality. Okay. And given that this example is both important and nice and geometric, let's sketch a proof of the Cauchy-Schwarz inequality as well, okay, which is this property of inner products. And we'll use geometry to see what quantities to calculate, but the calculations are fully formal. And so I'm not going to do all of them in detail. So let's draw a picture of the Cauchy-Schwarz inequality. We have one vector u like this, and then one vector v like this. For the sake of pictures, I'll draw them like this, though v could be much longer. We first assume we have disposed of the cases where one of them is 0, just by checking in that case that both sides are 0. Here is u and here is v. It need not be in this configuration, but formal things will work exactly the same. They don't assume this configuration at all. Okay, so theorem, this is Cauchy-Schwarz. Okay, so norm of, let me write this, u the v, and I can put a mod here also, but I won't bother because you can deduce that from here, is less than or equal to norm u times norm v. For all uv in Rn or any inner product space. So this is important, and the same argument will work for spaces of function, where we use a similar argument and so on. So then it works in many contexts. It's a geometric thing, but it works in great generality. It doesn't use the geometry. So what is the idea? Notice that if u and v are in the same direction, then their inner product is actually just the product of absolute values, the lengths, norms, which is exact. So we have equality. So but what happens in general, you are worse than this situation, and the way you prove this is we will take another vector, which is this one here, and use the fact that this one has positive inner product with itself, which by the way is a formal calculation. So even though, so what is this vector here? So this vector you can check is going to be u. I take u, and then I have to subtract some component of v, and you can calculate uv. Oh, so the u's and v's are too similar, so I'll have to rewrite that. So I take the inner product of u with v and divide it by the inner product of v with itself and multiply by v. Okay. Now just a quick check. If I take the inner product of this with v, the first term will be uv, and the second term will be uv by vv times vv, which these will cancel, and I get 0. So indeed this angle is 90 degrees. Okay, so indeed this angle is 90 degrees. So we have taken this, and the idea is that we just use the fact that this is non-negative. Okay, so a brief calculation will tell you that so the proof is that 0 is less than or equal to the norm of anything, so in particular the inner product of this with itself times v, which by the way, the fact that I'm sorry, it's not norm this, but not inner product with itself, u minus uv by vv times v. And now you'll get 3 terms, and the first term is going to be norm u squared, and the second term is going to be, well, we can square this side, but I'll be a little bit quick. So what we get here is v squared, not v into v, dot product of v with itself. Okay, and this v is looking to my u is looking, and the denominator will have inner product of v with itself squared, and so those will cancel, and I will be left with uv in both terms here squared divided by just 1 vv, and the last term will be minus 2 times the inner product of this, and again I have a u time, so when I take the cross term I'm looking at u inner product v, and I also have a u inner product v here, and so that's going to be uv squared, and I divide it again by vv. And if we rearrange this, we get norm u squared minus uv by norm of v. And there's a square here. I've probably missed a square somewhere. The first term has a norm u squared, and a simplification will give you the result. So the inner product is the norm squared, and therefore if I simplify things here, I will get, well, there has to be a uv squared here. I'm sorry, this is a square here. The square did not disappear. Therefore what we get is uv squared is less than or equal to norm u squared times norm v squared, and so indeed we would get actually the absolute value here, which implies without the absolute value as well. Okay, so this was an important example, so we did this in great detail. We have, however, seen maybe too few examples. We have just seen our usual spaces, and the point of metric spaces and topology is to generalize beyond multivariable analysis and also be able to deal with geometric situations. Okay, so that will be based on a class of examples, but first we'll look at a couple of more concrete examples, actually one more, and then we'll recall the other one. So if we had seen another example, so example we had seen was Sncf metric. So in this case, we have the proof by cases. So if you remember, this was an interesting case where I had the origin, which was rather special. Otherwise I took things in polar coordinates, and if I had edges that went out in different directions, and I had a pair of points on them, if I had things like this pair of orange points, one here and one here, then the distance was this purple line, because they were the same direction from the origin. On the other hand, if I had a point here and a point here, then the distance was going all the way to the origin and back again. Okay, and so there are a bunch of different cases that we have to consider here, and that those different cases will so those different cases you can do by, I will leave as an exercise. There's not particularly illuminating my doing it, but it's nice to do it yourselves. So this is going to be an exercise. And now here's one more concrete example. We saw the discrete topology. We similarly have a discrete metric. Okay, I'll define it. Again, the proof is an exercise, but this time it's a rather easy exercise. So discrete metric is one where if X is any set, just like discrete topology we can always define, you define distance of xy for x and y, little x and little y are points in the set X, is 0 if x equals y, as it must be, and 1 if x is not y. So by definition we have got the first property. It's symmetry because equality is symmetric. As far as the triangle inequality is concerned, you have to split into cases. If you have x, y and z, depending on whether x and y are equal to each other or y and z are equal to each other, in each case you'll either get equality or you'll get 1 plus 1, 2 on the side which is supposed to be bigger and 1 on the side which is supposed to be smaller. So this is again example of a metric. It's nice because you can do it on any set. So it's really, for example, it gives you for 3 points an equilateral triangle, for 4 a tetrahedron. So these are vertices of a tetrahedron, not the whole tetrahedron and so on. This is a useful example. This gives you the discrete topology in a sense that we'll soon see. There is no such thing as indiscrete metric because there we're forced to have all distances 0, which is not allowed. Okay, and final point here before we go to the next video where we'll see more is that we have not seen any really interesting examples except maybe a Sncf metric. What about a torus, a Klein bottle, an annulus, or Mobius band? All of these come by looking at subspaces. So they all sit inside Euclidean space. So really the large class of metrics come just from one simple construction, and that will be our next topic. But for now we have seen these concrete examples in detail.